Good morning, Salman.
Morning. How are you doing?
I'm good. Thank you. How are you?
I'm good. Thank you so much.
Good morning, everyone.
Good morning.
Good morning, everyone, or good evening, everyone. I think we should get started. Just a reminder, the link which I shared for the meeting, please bookmark it, although I mentioned in the message, because we'll be just keep reusing this link. And Salman, do you want to get started? I think you're on mute.
Oh, yes, definitely.
Oh, thank you.
Okay. For today, technically, it's mainly for beginners who want to kind of like understand the basic regression models. And so I would be kind of like showing you, first of all, basic simple implementations and the hyperparameter tuning part. So for example, like linear regression, there are not a lot of things to tune, but yes, there are some things that you can go and change and a little bit, and but there are not a lot of tuning required. But as the model kind of like gets complex and complex, like you get into random forest, then there are a lot of stuff you can a lot of parameters that you can tune, XGBoost or light GBM or gradient boosting. There are a lot of parameters. So, but I will start with simple basic linear regression, what exactly it is, lasso, ridge, the regularization parts, and then elastic net, which is kind of like combination of both of them. So it's kind of like that. Because we have several beginners in our cohort. That means if they don't understand the basics of those basic models, at least they would be applying those basic models, not that those fancy models that we are applying. So they should be kind of like doing something and learning something. So this meeting is technically what I would be talking about was mainly about it. So let me share my screen. And so these are kind of like what I did is basically it is a simple copy and paste of this baseline model. So what I'm talking about, let me show you that if you go to GitHub and you go to our repository, then you can go into the sources folder, and in the sources folder there are tasks folder, and then in the task folder you can go to task number 4, data pipeline, and these are the data pipelines. For now, for what I'm doing is I'm getting into the baseline one, and this baseline one has already data in it. So I will be using the data that I have created for the baseline pipeline. So what I did is I basically created another, so this untitled one, which I just created, it is just a simple notebook for just beginners. I would be breaking down. So there is a baseline model like this one, which is kind of like everything is combined in one big chunk of code. You don't know why exactly I'm calling so many imports and which one is what, or what am I using it for? Why means what is the use of grid search CV? What is the use of K-fold or things like that? So briefly, I will be breaking that down. So what I did is basically I just copied these initial things and now I would be breaking them down. For example, this is a lot of big chunk, but right now let's start. So I have already called in the data. So let's call in the data.
Excuse me, Salman, I have one question here.
Yeah.
If you're using Jupyter Lab for the first time, do you have to install pandas, NumPy, and all this stuff, or are they inbuilt?
If you are installing Anaconda environment, these all the repository, these all the libraries come pre-installed. But if you are not using or installing Anaconda and just installing Jupyter, I have never tried that. I just installed Anaconda. But if you do that, then you would have to install pandas and NumPy and all those basic ones yourself. But if you get the whole package, Anaconda package, they all these basic libraries, Matplotlib, Seaborn, or those things, they come inbuilt, built in.
Okay.
Yeah.
Okay. One more thing is, could you also go over how to get this into your local, like how to clone it? Like yesterday, what happened is I was using HTTPS only, but it was not letting me via VS Code or Jupyter or nothing. It was not letting me clone the repo. Yeah.
Okay, so tell me one thing. I recommended you to try to clone something from your own repository. Means if you have any repository on your GitHub, try cloning it. Is it working? If it is working, then your SSH connection and things like that, they are working fine. If not, then maybe you would have to go and update your SSH key and connect it with your GitHub. How to do that? There's a good YouTube video, means on Free Code Camp. I usually use that. So on YouTube, which one? Let me quickly share the link. Okay, so this one. So this video, you see, you don't need to watch this whole thing. You don't need to watch this whole thing. There's a chapter over here which covers the SSH keys somewhere here.
All right.
So this one, this particular section, I am on, technically I have bookmarked this particular section because this is somewhere I kind of like struggled when I started, and this is kind of like bookmarked for me. So I would recommend, so it has chapters, and which chapter it is?
Sure.
This one, about 20 minutes in. So you just need to watch the first 25 minutes of it, and it will cover all the basic commands and all the basic setup of Git. You don't need to watch the whole 1 hour video, but the first 25 minutes would give you a very quick overview of all the basic commands and how to set up the SSH keys, how to connect it, the local computer with the online GitHub and everything. So I would recommend just quickly go through it and means kind of like make another SSH key and update it.
Okay, thank you so much.
So I can share the link for this one.
Awesome, thank you so much.
Yeah, no problem. And now go back. Okay, so these are all the xtrain, xvalid, xtest, ytrain, yvalid, ytest. For simple reasons, I would get rid of the valid because I don't want to use 3 different kind of like, I will just use xtrain, xtest, ytrain, ytest. That's it. So I'm not doing validation whatsoever for now. I'm keeping it simple. Okay, but that is not a good strategy because what happens is if you expose, because right now I would be exposing my test data to the model while evaluating, while validating the results that I got from the training, from training the model, from using the trained data. What I mean to say is, it's kind of like the example last time I gave you. For example, if you are preparing for an exam and you have 10 sample exams available, you don't want to kind of like practice all 10 in order to prepare for the final exam. So what your strategy, because if you do that, then you have not validated your learning before getting into the real exam, which means you don't know how you would perform on an unseen test. So the good strategy would be that you would kind of like train yourself by doing 7, means you pick 7 exams, sample exams from out of 10, and you prepare using those 7. Then you leave only 2 to validate your results, means which you have not seen before. So you prepare using this first 7. Once you have prepared, now you attempt the next 2 which you have not previously seen, and see what kind of a results you got. Average those results out. That is going to give you an average validation result based on the preparation that you did. And if you want to use the last exam as the test set, then try that one and see that your accuracy for the first 7 practice exams was pretty good, but validation was a bit less and the test was a bit less, which means what happened here is kind of like you are not very well prepared for generalization, for getting good marks in unseen data or unseen test or something. So that is usually the strategy. So that's why you have to keep some data unseen through the model which model have not seen previously, because this way you cannot overfit the data. So that is what overfitting means you have used all the available resources and now you cannot validate what kind of a learning or what kind of a training you are prepared, or you have prepared yourself from. Can you deal with the unseen kind of situations very well or not? If not, that's what overtraining means. So we don't want that. For now, don't worry about it. This is just for beginners. Remember, again, we have a lot of people who have a very good experience. So please don't mind that I'm getting rid of the valid. We would be using the valid thing, but this is just for the beginners. Okay. So because I want them to do something and learn something and play around with at least a few basic simple things before they get into the kind of like whole different 6 set of data or 6 set of variables over here. So next thing is, these are a lot of kind of like chunk. What I'm going to do is I can create. Okay, so there are a few things you can use your keys. For example, you can see on Jupyter, it saves a lot of time. I'm just giving you shortcut keys for Jupyter that would save you a lot of time. For example, right now I'm in the edit mode. So my cursor is blinking here. That means whatever keyboard keys I'm pressing, it's going to write in this particular field. But if you are not in the edit mode, for example, you are in the command mode, how can you get in the command mode? You press escape button. If you press escape button, now you don't see any cursor here. You see a blue line here. This blue line is telling you that you are now in a command mode, which means now by pressing simple keyboard shortcuts, for example, if you press H key, means it's not giving, I think I have changed it. But for example, if you want to copy this particular cell, you press C key. Remember on computer, Control C is the copy, right? If I press C and if I press V for pasting, it's going to paste the cell over here by pressing just 2 keys, C and V. If I want to add another kind of like empty cell down there, if I want to do it below this particular cell, I would press B and it's going to create an empty cell below. If I want to create an empty cell above this particular cell, I'm going to press A. If I want to move cell up and down, I can use arrow keys to move up and down. This saves a lot of time because I hate going back and forth to my mouse. If I'm using my keyboard, I will keep on using my keyboard this way. So you can set up your shortcut keys like that. Technically, these are the built-in ones. I have been using built-in ones. I have not kind of like changed them. But these are a few basic ones you should remember. Now, if you want to delete a particular cell, you press D 2 times and it's going to delete the cell. And press D 2 times, it's going to delete the cell. You press A, it's above, and B for below. That means empty cell above, empty cell below. If you want to, so right now this is in the code mode, right? But if you want to write some markdown, right? What you're going to do, you get into the command line, press M. Now you see it has changed to markdown. And now press enter. You don't need to press the mouse in order to get into the command mode and edit mode. If you want to get into the edit mode, press enter. If you want to get out of the edit mode and get into the command mode, press escape. So these are the things you can go, and this can save you a lot of time on Jupyter Notebook. So Jupyter Notebook, it has a lot of good stuff, but this stuff makes you way more efficient because going back to the mouse and copying and pasting and things like that, it's kind of like a very time taking, and it takes up a lot of time. So if you are thinking fast and you want to implement really fast, this takes up a lot of time, and then you kind of like sometimes for me means sometimes I forget what I was thinking about. Again, what I wanted to write instead of. So in the beginning, I struggled with that, but then I learned these few basic keys, and now they're saving me a lot of time. Okay, so so for now, let's go back to the code. And for now, I did not figure out how to go back to the code. I can find it, but I did not spend the time on it. So, but for now, let's do that. Right now, I'm doing a simple linear regression thing over here. So I'm going to delete this. So for that, what we can do is we can from sklearn. So if you don't know where exactly linear regression is, you can always find linear regression sklearn. Sklearn is the library which covers whole bunch of machine learning models. Means if you are beginner, sklearn is one library I would recommend for you to go and explore for machine learning, and stick with that for once you have kind of like used a whole lot of it. Okay, because once you are good at it, you can understand any other thing, because TensorFlow uses exactly the same command line system like .fit and .predict and things like that. All those kind of like big deep learning libraries, they are kind of like built on the foundations of sklearn, you can say. So they use very similar pattern. So once you understand sklearn, technically you understand the industry standard way to model things. Okay, so I would recommend sklearn. So if you want to explore a particular model, write the name of the model and write sklearn. It's going to take you to the sklearn. So because I don't know, sometimes I forget what kind of means in which particular folder inside sklearn the linear regression model is stored. So here it is telling you that sklearn.linear_model, that's where linear regression is. So what I'm going to do is I will move back. Okay, so from sklearn dot linear_model, now I'm going to import linear regression. So you just write the name, and now I have imported linear regression over here. Okay, so if I press Shift Enter on Windows, I don't know about iOS, but on Windows, it's gonna kind of like run it. Now I'm gonna create new cells over here. Let's do that. And now I have linear regression. The first thing you do is now you need to instantiate the linear regression model. So linear regression. And I would recommend, for example, how to do that. Instantiate means you just call it and save it with a variable name that you want. I don't want to write linear regression, the whole word again and again. I can make spelling mistake, and that can make my code inefficient a bit, because I would have to kind of like go back and correct it. So I would just len reg, that would be the short form I can go with. Or if you want to just do linreg, just do it. Whatever name you want to give it, and you can type really fast without making mistake, just do it. Okay, so linreg, and then I would write linear regression, bracket open close. Now, there are some parameters you can write inside it. So what I did it over here is I went into the brackets and I pressed shift and tab. It gives me what kind of parameters I can put or write inside it. Do I want the intercept? Remember, linear regression is a simple straight line, a slope intercept form, right? Y is equals to mx plus c. What I'm talking about is okay. So what I'm talking about is so this normalize, it has been deprecated, which means if you have latest version, you won't be able to see that. But right now it is this. But if you cannot find it here, you can always go to, what I do is I always keep the sklearn linear regression handy. So since I have already searched for it, I will go, I can see, this is first parameter is fit intercept. It is a Boolean. By default, it is true. If you want it to be false, you need to define it. But if you want it to be true, you don't write anything. Since I have not written anything, I think I need to move my, so where is it? I'll just delete this. Just delete this. It's okay. So since I'm not writing anything here, that means I'm using all the default parameters. But if you want to write something else here, if you want to write something else, for example, copy X. What is copy X? Copy X is, for example, you have seen that in my code. What I do is basically, if I'm copying a particular data frame, for example, when I was dividing the X variable from our original data, I was doing something like this, that X is equals to, let's say, X underscore train dot copy. Okay, so something like this. Does it give me an error? So copy. What I'm doing here is, when I do not do copy, what it does is basically, wherever in the memory X underscore train is being saved, I'm just changing the name for it, and I'm assigning it to capital X. But if I do a copy, I'm making another copy of it. And it is technically, sometimes you can also do a deep copy or something, but that is just for the memory and those things. What it does is basically, it does not do anything to the original data, which means you cannot corrupt the original data or change the original data in this particular manner when you do a copy thing, which means whatever you do to this capital X, it's not going to do anything to your original data. So when you are doing these things or transforming your variables X or Y or something, it's better to make a copy and do all the transformations on the copy and keep your original untouched. So that way your original is always for the reference out there, and you can always go back to the original version if you ever want to, if you kind of like, for some reason, kind of like destroyed this X and something. So it's kind of like a good practice to do that. So but right now, let's get rid of it. First thing, you instantiate it. After instantiating, you can start fitting it. Over here, you can see that here I was doing a lot of kind of like models. So this is linear regression, the first one, and here I'm timing it as well, because when you are making models in real life, you also want efficient models. If some model is taking too long a time for training and everything, model complexity is something which you can determine based on the timing, how much time it is taking and things like that. Because if you are running it on cloud, you would be getting means if it is running for 1 hour, you would be getting charged for 1 hour. If it is running for a few seconds, you would be getting charged for those seconds. So money is kind of like a concern as well. So that's why timing the model. And for example, if you are competing on Kaggle or something, Kaggle gives you very limited usage of GPU and TPU units and everything, and you don't want to kind of like use it without timing and without making it less complex and things like that. If you go on Kaggle, you would see a lot of people using garbage collectors, GC and something, in order to reduce the memory size, running speed and things like that. Right now, we are not getting into that, but you would see it. When you see it, don't get confused by it. You can, for now, as a beginning stage, you can just ignore that. So right now, I would not be looking at the timing thing, maybe later. But right now, next thing, what we have to do is we have to fit the model. So fitting the model means you need to train the model on. So it's kind of like the example I gave you. You have 10 sample exams. Now the first 7 sample is my X train, and now I want to train my model. So what is that particular, in that particular example, what is happening is, you know, for example, if it is an MCQs based exam like SAT or GRE or something, then you already know what would be the answer of question number 1, whether it is option ABC or whatever. What is the answer to 2? All those answers are your Y variable, and all those questions are your X variables. So when I say X underscore train, then what I can do is I can do lin reg dot fit. Now, first I instantiated this, and now I'm training the model. So I can write model. Linreg, I'm fitting. Now I need to give X variable and Y variable. If you don't know how to do it or something, you can always go back here on the sklearn and you can find it. There is usually a solved example everywhere. You can see first they instantiated it. Over here, they did it in one single go. They instantiated it and fit it in one single line. You can do that. So in Python, this dot notation kind of like you can keep on adding dot and it keep on getting a nested kind of like a thing. It will do the first thing, then the next thing, then the next thing, then the next thing. So if you want to do it in one single go, you can do it. If you want to do it separately, you can do it. Why I'm doing it separately? Just my choice, because I want to kind of like break it down into steps. Otherwise, I can do it that way. Breaking it down into steps this way gives me the opportunity that I can assign it in a list, and then I can run a for loop, which I did in the baseline model over here, that I ran a for loop, and now it's going to go to the first model in the for loop, second one, third one, fourth one by one. So that's why breaking it down like that in these situations would help. Right now, I'm just doing it separately. That's good. Now I would write X underscore train and Y underscore train. When I press it, run it, what it's going to do is it's going to start training. You see, when you see this model has been trained, and if I had some parameters inside it, it's going to give me. So when you get this result, that means now your model is ready to predict. So which means it has already seen all the data points in the X train, and based on the Y train, it has learned all the parameters. So what happened over here is, you can all see my screen. So what happened over here is technically, let's say we have several different features, right? So let's say we have kind of like a coefficient multiplied by feature number 1 plus a coefficient multiplied by feature number 2 plus, and so on. Our data has so many features. So that is what is happening. And then finally, there is a y-intercept. So what linear regression does is it basically plots X versus Y, and there are data points all over the place. And what it does is it picks out a line of best fit. This point where exactly it is cutting the y-axis is the y-intercept. And the slope, what is the slope? In simple mathematical terms, which you have learned in grade 6 and 7 or 8, rise over run. That is what these coefficient values are. So you need to figure out the coefficient values we call them gradients, and in school we used to call them slopes as well. So gradients, slopes, derivatives, they are one and the same thing. So these are all the names which kind of like we used interchangeably. When you start algebra for the first time, we start with slopes, then we get into derivatives, and then we use a very, very technical name, gradients. Okay, so technically this is what is happening. This is the rise and this is the run. And what exactly they are change in the y variable over change in the x variable. That is what the slope means. So what linear regression did is it figured out this plot and figured out the line of best fit, and it figured out what would be the slope of that line and what would be the y-intercept. And the general equation of this particular equation in terms of one feature is simply mx plus b. This m is the slope, this rise over run thing. And this b is this particular point, the value it is cutting on the y-axis, means whether it is cutting at value number 1. What does y-intercept means? Y-intercept means if you are putting your feature value is 0, your model is going to throw in some result anyways. In machine learning lingo, we call it bias. In mathematics terms, we call it y-intercept, but in machine learning lingo, we call it bias. And bias, why bias? Means if I put x value equals to 0 here, this whole thing is going to get to 0. And my answer is still going to be equals to b, this bias. That means it is the noise which always is in the model, which is always there. That means no matter what you do, you will get a result, an output equal to that. Means even if your all the features are 0, it's gonna throw in a non-zero answer, and that non-zero value is technically the bias in the model, or the noise in the model, you can say, which is always there, and we always have to include it in our models. Okay, so that is what is happening over here. So when I trained it, now my model is ready to predict. How can I predict it? You can see what I did over here is the next thing I called is this prediction thing. For some reason, my mouse is. So this prediction thing, right? So how does this predict work? Let's write. So now linreg is my model. I do predict. And now when I'm doing prediction, I am giving it, for example, all the remaining x values the model has not been trained on, like the test data. And I already have the answers for that. What I'm going to do is I would be comparing it with the original answer. So I would be predicting using the model, and then I would be evaluating my model by comparing my results and the original results. So prediction is generating my results, the model's result. Okay, so that is the step what we are doing here. So when you do linreg.predict, and here predict on what? I need to give some input. Here I'm doing the test data. So I would be predicting it on the test data. So I want the prediction by the model, and then I would compare it with the original answers. So I'm going to give it a name. I would say y_pred. That is the variable name I usually use. Some people use it y hat. Some people use it y prediction. Some people use different names. But if you stick with one particular convention, usually it saves you a lot of time, that what name you should be giving to your variables and everything. I would recommend just make one particular convention and stick with that convention. It saves you a lot of time in thinking about variable names. So when you do that, it's going to predict. Now this y_pred is technically, if I print it, it has all the y values. You see, it is giving all the y values. I already have the original y values in this y_test. What I can do is I can compare side by side, and I can see what kind of a difference there is. Is there any difference? And that difference is going to tell us how good my model has performed. Okay, so what I did over here after that is I'm looking at all these. So so how much explained variance score is basically how much of the variance of the data was explained by my model. So our every single feature is bringing in some variance in the data, some kind of like disturbance or some kind of like variations in the data. How much variance? I want to kind of like cover as much variance of the data as possible. My model would be good if it can cover more variations in the data, or it can generalize to higher amount of or bigger value of variance. So that is our usually goal is. Mean squared error is basically what happens here is it's kind of like several different things over here. What happened here? So what happens here is, for example, this particular line, this particular point was this point away. This particular line was this length away. This particular point was this length away. This particular line was this length away. What we do is we basically find the distance between every single point from the mean or the line that model has predicted. We kind of like add all the differences, all these distances, then we square them. After squaring them, that is what we call mean squared error in simple terms. Now, there are so many different distances we can use. This is one of the distance some people or some models can use, but there are sometimes the perpendicular distances also used. So those perpendicular distance are kind of like a bit advanced things, because calculating them is a bit complex, because if you do these perpendicular things, they are also, so these vertical lines are only looking at the y variable, because it is telling you how much away in terms of the y variable I am from the original thing. But when you do the perpendicular line, it has a slope, which means if this particular point has this line, that means this line has a slope, which means it is also covering some variations in x as compared to y. So there are some distances. When you go and explore several different parameters inside the models, if you know the theory, then you would know that what every single parameter means if you are doing hyperparameter tuning, these are the things you change, and you can see whether your result improved or not. Okay, but for now, let's stick with the vertical lines, and that is what the mean square error does. So mean square error. So what is root mean square error? So we are not doing, so over here, this one is the root mean square error. So what I'm doing is, if I have kind of like find the errors, added all of them up and squared it. If I take a square root, it would be root mean square error. That is the only difference between root mean square error and mean square error. Now, mean squared error, if I tell you briefly, I don't want to go in detail because that would be a whole complete topic about them, because that's it. But mean square error and RMSEs, they are inclined. If you have outliers in your data, then these are not good measures because they get affected by those values a lot. For example, if I have a point over here, which means when I am finding, so this is the value of my feature X, and this is the value, which I would call it mean, let's say. So which means what I'm doing is I'm finding the distances, for example, X minus X bar, or maybe Y instead, I would be doing Y minus Y bar because these are vertical distances. So this is Y and this is my mean value. So what I'm doing is I'm finding Y minus Y bar for the first point. Then I'm going to do it for the second point. I would start with 1 until n, and y is equals to I. And so what I'm doing is I'm going to the first point and I'm finding the difference between the first point and the predicted line. Then the second point, and then find the difference from the predicted line. Then the third one, then the fourth one, and keep on adding. When I'm adding all of these, if this is an outlier, this distance would be too big, right? And while I'm adding all those differences, that big difference is gonna make the whole sum really big, right? And when I'm doing square, which means, for example, my error turned out to be 2, but if I'm squaring it, that is 4, which means, first of all, I originally maybe was getting means 1.1, but because of the outlier, my result was 2. And when I squared it, my mean square error turned out to be 4. But what if it was originally 1.1 and that outlier kind of like make it go to 4? But if you square okay, so I will anybody who joins late, since it is getting recorded, because I want to get done with that. Um, okay, so that is, so what I was saying is, for example, my original error, if I get rid of this point, should be 1.1. But since I have this in my data, it ended up giving me my error calculation to be 2 when I did that. And then when I squared it, it turned out to be giving me 4. Now let's see if it was 1.1. If I was able to remove this point, then if I square 1.1, that is going to give me 1.21, I think. Which means look at the comparison between the differences between the errors that I'm getting because of the outlier, which means if you have outliers in your data, then RMSEs and mean square errors means mean square errors is going to be 4, root mean square error is going to be 2. This one is a bit closer to this. So which means if I want to use this mean square error thing, I would be using root mean square error instead of mean square error. So which means when to use which metric or which evaluation metric is usually in the background. You need to know this thing, why exactly I'm doing that. Okay, if you do that, it would make your life pretty easy. Means in order to determine when to use mean absolute error, which I did not talk about here. So what is mean absolute error is it's very similar, but it is not prone to outliers. And just to keep it short, I would kind of like go deep down on it, means some other time. But for now, I think Rich has already covered this in one of the YouTube videos that he has created for one of our channels, Autodidact Scientist. You can check that out in order to go in all the evaluation metrics for regression, since this is a regression problem we are dealing right now. So you can kind of like take a look at that video. So but these are the errors. Now let's go and implement them on sklearn. So if I go here and I want to implement it, so first of all, I want to bring them out from the sklearn library, and I don't know where exactly they are. I'm gonna do exactly the same thing I previously did. I will write let's say root or RMSE sklearn. That is what I do. And that's where it is telling you that you need to get into sklearn.metrics, and from there you can call mean squared error. So that is what I'm going to do. I will just go here from sklearn.metrics, import mean squared error. I wrote everything right. So metrics mean underscore squared error. Yes, that's right. It should work. Let's try it. So it's good. Now I have the error metric. If I want to use this error metric, I can do that. Means, first of all, if you don't know how to use it, you can always go here and you can see what are the parameters. It takes in the true values of the y, which is our y underscore test. That is the true values. And then your predicted values. You see over here, y underscore pred is the variable name that sklearn uses. And that's where I learned it from. Means I give it the same name so that I know where to put which variable. Okay, so that is what I'm going to do. I will just write mean squared error. And then I would put in the original y, which was y underscore test. And then I'm going to throw in y underscore predicted one. And I can run. You can see it gave me what is the mean squared error on my data. This is exponent 17, which means it is a pretty big number, a very big error. That means my linear regression model did not do really well. So, but similarly, now there are certain things that you can do. If you go to linear regression, there are certain things like there is some regularization. You see, it tells you there are different versions of linear regression. How do I come across different models? I mean, so many models. If you go to one single baseline model, it's going to tell you there are other models similar to that. Ridge is one of it, lasso is one of it, elastic net is one of it. What exactly they are? What they are doing is they are regularization. They apply some penalties. So right now, the simple linear regression models, I'm just using it as it is, okay? But what this ridge and lasso do is they apply different penalties, and we name them L1 and L2. Okay, so we call it L1 regularization, which is used in the lasso. What exactly it does is it basically reduces the effect of a particular variable to 0 if it is not important. That is what it does. It penalizes some of the variables which are not doing a lot. And what ridge does is basically reduces the coefficient size of, means if, for example, while calculating the regression, the coefficient size of a particular variable is too big, it will try to squeeze it and bring it to a smaller number. So it kind of like protects it from exploding or getting these big numbers. You see, this is a pretty big number, exponent 17. If I apply those regularization, it can reduce those coefficient sizes, and I can end up with a small answer. So maybe let's apply it. What I'm going to do is I will apply ridge regression. So let's open ridge now. So how to call the ridge? It is exactly in the same class as linear underscore model. I'm going to go here and I'm going to run it. So from sklearn dot linear underscore model import ridge. I'm going to import all of them out, lasso and elastic net. So these are the did I write it correctly? Elastic net. Yes, I'm good. So ridge, lasso, and elastic net. Okay, spelling mistake. Okay. Elastinet, I think. No? Did I do something wrong? Okay, let's double check the names. Elastic, okay, N is capital, so let's make the N capital. So we have these three models now. We can do exactly the same thing. I can call in, let's say, ridge is equals to ridge. I will call this. Then I will instantiate lasso as well. Lasso is equals to lasso. And then I will, why am I writing lasso? And then I would be doing, so E net. I don't want to write the whole thing. So let's instantiate them. So that is what I'm going to do. Now let's fit them individually and see what kind of a result I'm going to get. So I would just fit the first one. Let's fit ridge dot fit x underscore train comma y underscore train. You see the pattern is exactly same. I will train it. And then I will also do with the lasso as well. Dot fit, and then I'm going to do x underscore train, y underscore train. Then I'm going to do e net dot fit, and then I'm going to do x underscore train, y underscore train. Now it has fit all these models. So what it does is basically it prints the last one. Usually if you want to print it out for every individual one, you have to use the print command. Otherwise it is just in giving the output from the last printing command in the notebook. Now I can predict the answers. So now I'm going to do y underscore pred underscore lasso is equals to maybe I can start with y underscore pred underscore ridge is equals to ridge dot predict, and then what we did over here when we predicted it over here, x underscore test, I'm going to do exactly the same thing. Excuse me. Similar thing, I'm going to do it over here as well. And I'm going to change the name lasso, and then over here y underscore pred underscore enet dot predict x underscore test. So now I have predicted. Now I have 4 variables. Let's run the mean squared error on them. So what I'm going to do is I'm going to paste it multiple times. So first one is, so y test, and then this spread. First one is the ridge one. So let's print it out. You see, from exponent 17, the value has gone down to 0.67. That means I have reduced the error by penalizing the big coefficients I was getting for the linear model. So I was supposed to get the small answer, and I'm getting the small answer. Let's see what Lasso gave us. So I'm going to copy the same thing, and I'm going to add Lasso 0.95. So I'm getting a higher error. That means in this scenario, Ridge did better than Lasso. Okay. And then I can add maybe ElasticNet. What ElasticNet does is it uses the combination of Lasso and Ridge. L1 and L2 regularization both combined together. That is what ElasticNet is. Okay, if you have never heard of the name before, it is simply a combination of Lasso and Ridge together. You can say an ensemble of it. Okay, so if I copy it here, underscore enet, it's gonna give me 0.95. That means the best error, the smallest error I'm getting is from the Ridge. So Ridge should be my model to go about, and I can go and I can kind of like get into fine tuning the Ridge model. So how can I fine tune? These are the kind of like parameters you can adjust. You can maybe change the fit intercept to false. Try it. You can maybe try this. I think it has been deprecated, but if you still want to try it, if you have a previous version, you can try it. Maybe it has been changed to fit underscore step or fit, I think, before calling fit or something. Number of jobs is simply telling how many processor cores you want to use, or threads or cores or whatever. So if you want to use all of them up, -1 is basically tells you. So number n underscore jobs is equals to -1 means use all the cores in your processor. But if you want to use just 2 cores for this particular training and save some of the other cores in your processor, if you have more cores, you need to know how many cores you have in your processor, and then you can use it for maybe training other model or something, or maybe doing some stuff. Otherwise, the whole if you do -1, all the processing power is going to go get into training this particular model. Then positive means if you want to keep the result always positive, you can do that. For example, when you go to cross validation or something, they usually use the negative version of it. So right now it is true, but if you want to make it negative or false, you can do that. There are not much you can do over here. For example, like these are the methods that you can use. If you want to predict or get out all the parameters that you used for this particular prediction, you can do that. For example, if I want to do, for example, ridge dot get underscore param. Did I do something wrong? Get underscore params. So you see, it is telling you that I'm using technically bound method base estimator, and I'm using all the base default parameters. If I was using something different, it would give me something different. If you want to score it, you can also score it. Return the coefficients of determinations of the predictions. If you want to set the parameters of this estimator, you can use it. So these are all the things. These are simple basic models for now. If anybody has any questions in this introduction, I know that a lot of people already know this stuff, but for beginners, if you have any questions, or even anybody who wants to ask me questions about this, please ask me. I just wanted to cover some basic, because if anybody is getting into machine learning, these basic models is what you should start with and get start doing something. Yeah. And I.
Do you think like in line 13,
Mhm.
you don't need to put it in variables? Like a bit,
So
yeah,
you.
like
So you were
we
saying.
don't have to.
Mhm.
Mhm.
Yep, can you complete your question? Then I can answer.
No, I'm saying maybe you will save it in the variables and then call it.
Oh, yes. If you want to save it in a particular variable, you can do that.
Yeah.
Yeah.
And then you do like the variable that predict, right?
Yes.
Or not?
Yes.
Yeah.
Since
Okay.
I have already done that here, I don't see why I would be doing it.
Oh, okay. This is the variable. Like
Yes.
read. Okay.
So since I have already done it separately here, that is what instantiating means. This way you don't have to write all the model parameters and everything. So what you can do is, for example, over here, that XGB regressor, if I want to do this, then what it's gonna do is, for example, I'm gonna create. So for example, if I want to write this over and over again, I don't want that. What I'm going to do is, when I'm instantiating it, I would just instantiate it and save it in XGB. And now I want to do XGB.fit, and that would save me a lot of time. So if you want to write all the parameters and everything all in one line, you can do that and then save it in one variable and just use the name of the variable. It's going to call the whole thing. So yeah.
So here, connecting question to this is, suppose you have instantiated XGB here in one, the baseline model, let's say. So when you're building the other models, you can just use XGB, or you would have to initiate it again with every notebook for the same data, because you have all of them in one folder, right?
So in one, so this is what we call kernels. For example, if you have in one notebook have instantiated one particular model, and you want to use exact same parameters and exact same specification of that model, you don't have to instantiate it again and again. You just keep on using the variable name that you have stored. For example, like if this is exact model you need to use several times to predict or doing some stuff, then you don't need to instantiate it again and again. One time is enough. But if you are changing the variables here, the parameters in here, then you need to instantiate a different version of it again and again.
Right, which means in another notebook, in another model, if I'm running XGB, I like your notebook. Suppose I ran some other model pipeline and it has XGB, but then if I run it as the first time, it could show as XGB is not installed or it's not found, right?
Mhm.
Okay.
So that is where you need to import it first. So if you are opening it and doing it in a new file, for example, in this particular notebook, I have already called in linear regression and lasso and ridge, right? But let's open another notebook, a blank notebook. So if I open a blank notebook and I have used, since I used linreg and I call it, it's going to give me an error that there's no such thing as linreg. I need to do all the steps all over again. I need to go and import the exact model I want to use from exact particular location in the library, and then instantiate it, and then give it the exact name that I want to use. And then, so every new notebook, you would have to kind of like instantiate everything all over again.
Every new notebook. Okay.
Every new notebook. But within one particular, for example, since I have already called in ridge, lasso, and elastic, right? And I have used it here. But if later, let's say I want to use it again, let's say over here, I don't need to import it again. It has already been imported. So it is part of my kernel. So, I don't need to import it again. One import is fine. That is the reason why what we do is we basically usually do all the imports at the top of the notebook. And if you see a lot of notebooks, they do all the imports at first, all of them. So over here, you can see anything that I was using, I just imported it one time. And then I just keep on using them because I know that I'm not going to get any errors, because whatever I'm using, it is already part of the kernel of this particular notebook.
This notebook, okay. Which means if I just take your notebook, this one, and without writing anything myself, run it, then I should not have any error.
You should not, as long as you have the data in the required folders. Over here, you can see that
/data.
yes. So so what exactly I'm doing here is this dot
current folder.
Current folder. Yes,
folder.
absolutely.
Within that you have the data folder, and within that you have the actual data.
Yes. So I'm getting into this folder. So I'm telling it to go to the current directory, get to the data folder, and in the data folder, pick up this particular CSV file. This one.
Got it. Thank you.
Yes, Divya, you're good to go. If anybody else has any questions, please feel free to ask. I wanted to cover
I have
more,
a question.
Yes,
So every time this linear regression model is going to give error, high error, so we'll end up using this three models, the lasso, ridge, and elastic net.
These are a few penalties. If you want to kind of like go and add a penalty into the linear regression model, where's my model? You can do that, but these are some basic models. That is where, okay. So you see all these models that I have written here, they are doing regression. They are doing exactly the same thing, but how they are doing it, it's different. For example, like if we talk about K near neighbors regressor, what it does is I can give you a quick sneak peek about it. For example, so if I go over here, so it's kind of like that. What K nearest neighbor does is it uses the distance formula, which maybe you have learned in grade, means I'm a high school teacher. I know that which grade we introduce in. So I know that it usually gets introduced in grade 6 or 7. The distance formula between 2 points. If you have 2 points on a particular X and Y plane, for example, this is one of the point X1, Y1, and this is the second point X2, Y2, and I want to figure out a straight line distance between them. Now, K nearest neighbor has a hyperparameter here, this distance. There are so many different types of distance. This straight line distance is called Euclidean distance. There are so many other types of distances, Minkowski, or so many different. That is what you can play with, which distance can give you better results. That is one of the hyperparameters for KNNs. But right now, let's stick with the Euclidean distance, the straight line distance. The distance formula is usually what? You find x2 minus x1 square plus y2 minus y1 square, and then you do this. That is the distance formula over here. This is what it does. So what it does is, for example, in our data, we have a lot of features. Let's say this is x1, this is x2. Let's stick with x1 and x2. And then we have a few things that I want to predict, maybe the y variable or something. So for example, I train my data. What it does is it's basically when you throw in a particular X variable or data that you want your results onto, what KNN does is it basically figures out the distance between the point that you have thrown in using this formula. So for example, what is the distance from the feature 1, feature 2, feature 3, feature 4, feature 5? If we have 60 features, feature 60, add the distance and assign the distance to that particular value. So when we use 5 nearest neighbor, that means what it does is basically it calculates the distance from all the data values that you have, and it gets close to the 5 nearest, that means whichever is the closest to the distance that your data is having, it picks out those values technically, or averages them out, and that is what the prediction usually is. So k nearest neighbor in the background uses a simple formula we kind of like got introduced when we started learning algebra. So that is the simplest basic formula that is being used here. For example, it figures out from one of the x variable what is x1 and y1, and it so you are inputting some y and x value, right? So it gets the nearest number. So if k nearest number, or the number of neighbors you are doing is 3, it would look close values to to the 3 nearest neighbor. If it is 5, then it is 5. If it is 10, it is 10. Then it will average it out. So that is what it does. So every model in the background is doing some sort of a different stuff, and that's where you need to know the models, some sort of mathematics behind it. Then you would understand what things I can play with. For example, like which distance to use. For example, like when you are tuning the hyperparameter, knowing what kind of a distances are available, that's amazing. For example, recently I was looking at one of the posts which I really liked. I can share it maybe with you. So there are so many different types, like Euclidean distance, cosine distance, Hamming distance, Chebyshev, Minkowski, Manhattan, Jacquard. There are 10, 12 different types of distance out there to play with. Yeah. Anybody else has any questions, please feel free to ask. So
if we're going to a scalar and then like k neighbors regressor, so we will see all the variables, like all the distances, right?
So you will not be able to see. Means that is where it is doing in the background all those things for you automatically. For example, when we are doing the training, right? So the training part is where it is calculating all the distances, and it is giving you the kind of like, since it has already calculated those distances, now when you are, for example, predicting the answers, what it does is it goes and it picks out the 5 nearest neighbor and average out and give you the result. That is what it does. So if you want to get it out, I never tried it. Maybe you can do it, but I never bothered trying it.
No, I mean the Euclidean and the others, like the options that we have. I want to read about, to elaborate more reading about it. So if we're going, we will see all the options that we have, right?
So let's see. So over here you can see, yes. So how many neighbors you want to pick? What algorithm you see? These are different algorithms. There is a brute force, there's a KD tree, ball tree, auto, several. You can look at that. And then where's the distance?
It's the classifier. Is it has a difference?
Sorry.
If you're looking at a classifier, not a regressor, is it a difference?
Yes, classification is a different, whole different.
Yeah, go a bit up. Go a bit up.
Means all these models that we are using, for example, linear regression cannot be used for classification, but logistic regression can be used. So classification means when you are predicting how many categories in your vibe, means whether it is a dog or a cat, right? When you're doing that kind of a stuff, when you need exact answer, not the real numbers, then that is classification. Means you either want 1 or 0. You either want 1, 2, or 3, that is classification. But if you can have real numbers like 1.2, 1.3, for example, in our case, we are predicting site EUI, right? And that number is a real number. That means it can be 4.5 or 7.2 or 50.5. That means that would be a regression model. But if it was 1 or 0 or cat or dog, or whether it is human or not human or something like that, that would be a classification. So the models work differently for classification because here we are using probability. Over there we are kind of like using a threshold. There are some differences.
Yeah. Salman, I'm sorry, you are looking at the page of k neighbors classifier.
Oh, sorry, my bad. KNN regressor SK. The parameters are pretty much same for both of them. For example, you see the parameters are
Oh, okay. This is what I was asking. Okay. Okay. So
parameters are pretty much same. In the background, the model is different.
Okay. Okay. Mhm.
Not a lot, but a little bit. Yeah. For example, over here, you can see the metric Minkowski. We can change it to Euclidean. So these are the distances
Okay.
we can change. So these metrics. Yep. Anybody else has any questions, please feel free to ask. Otherwise, we will wrap it up. I think everyone's good. So I think for today, that is what I wanted to do. Yes, please go ahead.
Is it possible to ask something about decision tree regressor or not? Or it's in another lecture?
Say that again. No?
Am I like, is it okay to ask about the decision tree regressor, or are you going to cover it in the next lecture?
I will be covering, because these are so many models, I cannot cover them in one single go. But decision trees, you can ask me questions right now if you have any. But I will not be breaking it down right now. Maybe later.
Okay, I just like wondering about all of this, like how decision tree can be a regressor.
How decision tree can be a regressor. So that's a good point.
Like it's a classifier, no? Like it's decides like, or this branch or those branch, and that's it, no?
So that's where I'm telling you that probabilities, when you are technically every single model over here, they are calculating probability of something happening. And
okay.
For classification models, what we do is we set a threshold and we say that if the probability is above that, then it is a cat. If it is below that, it is a dog. But we can use the probability part of it in order to make it into a regression model. So in the background, that is the difference. So any model that you're using here, that's why they can be used as a regression or a classification part.
Okay, like we will have like a scale.
Yes.
Of numbers, or we can do a threshold that will like cut it, or left or right. Okay.
Yes, yes, that's right. It's kind of like when you are flipping a coin, right? We have a 50% chance. So for example, for some reason means if I want to pick a particular stock or something in order to invest, means if I know that I always pick 60%, means if it is performing in a particular range, I have a number in my head. If it is performing above that, for example, like moving average, 50 days for moving average is above that, I'm going to buy the stock, otherwise I'm going to sell the stock. So it's kind of like a decision making. So I have set a threshold in my head, but that's what they do. They already are calculating the probabilities. But if you use a threshold and define a threshold and tell it that give me the result only if it is above it or below it, we don't care about what the value is. That's when classification happens. But if we care about the value specific, that is regression.
Okay, I understand. Yeah, thank you very much.
No problem. If everyone's good, I think back to you, Imran.
Thanks, Salman, for this demonstration. And one quick announcement for the groups, for team leads and co-leads of other teams. We understand there's a different time slots. You guys, all of us will have different times for our respective for our respective teams. But that's also a possibility. There are other participants from other teams, but they would like your stuff to attend, but they couldn't because of different other commitments. So it would be helpful if you can please record your meeting and just share within either your Slack or wherever you want to post it. Just announce within your channel, so at least if others want to watch, they can watch it and learn too as well, right? So please make sure all task leads or co-leads make sure of that part. Okay, that's it from my end for class. Okay, guys, have a good weekend. Thanks for coming.
Thank you so much.
Thank you. Thank you.
No problem.
Thank you.